Hi, my name is Raven. The topics that I'm going to present today is on the cellular architecture and key technology for 5G wireless communication network. There are three main things which I will be covering in this 15 minutes presentation. First, I will have a quick introduction of the motivation for a 5G network. Next, I will be talking about a possible cellular architecture that could be deployed for 5G network. And subsequently, I will be discussing some of the interesting technologies that have been identified for the 5G network. There have been reports on rapid growth of wireless devices every year. Wireless World Research Forum predicted that in 2017, there will be 7 trillion wireless devices around the world to serve the entire 7 billion population. Sooner or later, the current capacity of the 4G network will not be sufficient to handle the explosion growth of wireless devices. Also, the crave of faster internet access and advanced multimedia capability on smartphones have driven a greater needs for higher data rate. However, there is limited radio frequency spectrum allocated for cellular communication. Hence, we need to pack more data bits in per hertz bandwidth. Squeezing more bits with same amount of bandwidth will incur higher bit error rate, and to reduce it, higher transmission power is required, and this will result in greater energy consumption. The battery life of your mobile devices will drain faster, and not only that, it also causes higher CO2 emissions, which have been identified as a major threat to the environment. With all these primary considerations, this leads to the motivation of 5G network, which will be deployed in the near future year 2020. So let's take a look at the conventional cellular architecture. Basically, we have an outdoor base station that is built in the middle of a cell, and all mobile users within the cell communicates with the base station directly, regardless whether the user is inside a building or located outdoor. For user inside a building, signal going through the thick concrete wall will suffer a huge penetration loss, which result in lower data rate, poorer spectra, and energy efficiency. So, a possible 5G cellular architecture has been proposed to separate the indoor and outdoor usage. There are also research shown that wireless users stay outdoor for 20% of the time, and the remaining 80% they are staying indoor. Hence, it might be more appropriate to have a mini base station inside the building with distributed antennas for individual floors. This concept is known as femtocell, where the user device will communicate with this mini base station through these distributed antennas, and the mini base station will then communicate with the outdoor base station. This avoids the penetration loss through concrete wall. It also shortens the communication distance and hence uses less transmission power. There is a various way of providing signal into the building. Typically, distributed antenna system, also known as DAS, is a popular way used to extend cellular services into buildings or facility where it is highly populated. With the use of DAS, it will ease the workload of the outdoor base station and shorten the communication distance. This will in related improve the spectra and energy efficiency. Now let's take a look at how DAS work. Typically, we will have a cell tower, also known as base station, that can cover larger area. DAS is installed inside a building as shown in this slide. The service provider head end converts the signal to digital and transmit optically over fiber to the remote antenna unit at the individual floor inside the building, and which are in turn connected to small low power antennas. These distributed low power antennas are spread out across the floor to guarantee coverage within the building. Modern DAS typically use fiber backhaul to connect to all wireless service providers, although it still can use coaxial cable to connect to the outdoor antenna and communicate with the base station. Using fiber backhaul will be a much better option as it is wired connection. This definitely will achieve higher data rate, increase reliability, avoid the use of limited radio spectrum, also minimize interference over the air, and easing the workload of the base station. For DAS, it covers a small area, hence antenna is low powered and service fewer users. Servicing fewer users means that there will be more bandwidth available for each user. This works much better for those users using data video service over their mobile devices. Besides the use of femtocell, there are also trends in using smaller cell within a bigger cell to enhance the system capacity. The concept of overlay cell is also known as the heterogeneous network. This concept was proposed in the framework of LTE Advanced to increase the spectral efficiency. Since radio link performance is approaching the theoretical limit with 4G, network topology seems a way to increase system performance. In this strategy, macro base stations are used to provide blanket coverage. On the other hand, small low-power base stations are introduced to eliminate the coverage holes and at the same time increase the system capacity in hotspots. Furthermore, heterogeneous network provides an opportunity for network provider to optimize overall cost, revenues, and customer satisfaction. So, macro cells are mainly used to provide a widespread coverage area, but they can only support low data rate services. One obvious approach to make the cellular network more power efficient and thereby sustaining high-speed data traffic is by reducing the propagation distance between nodes, hence reducing the transmission power. Therefore, network deployment solution based on small cell is very promising in this context. A typical heterogeneous network deployment with smaller cell structure can be used for providing high data rate services to smaller areas with a high density of traffic. Micro picocell can cater to many devices within range of a few hundred meters, while femtocell are mostly used for indoors or home area. Due to their short range, femtocell are more power efficient and are usually used for private indoors communication, often wired directly to a private owner cable broadband connection or a homeowner DSL. Heterogeneous networks are also increasing the energy efficiency of the network and hence considered as a promising trend toward holistic green communication and networking. However, easier said than done. There are more issues that require deep consideration and has to be looked into, like defining how these different size cells are going to work together, how to achieve an efficient handoff among them, how to minimize interference among them, and how spectral and energy efficiency will be optimized. However, all this will not be covered in my presentation due to time limitation. Here comes to the second part of my presentation. What I will do is to quickly cover some of the promising technology for 5G network as listed in this slide. As we all know, cellular communication is using ultra high frequency that range from 700 MHz to 2.6 GHz. Sadly, this converted spectrum has been heavily used, and as mentioned many times in my presentation, 4G network have just about reaching the theoretical limit on how many bits they can squeeze in a given amount of bandwidth. Hence, people have been looking at transmitting signal at extreme high frequency that covers from 30 GHz to 300 GHz. It is known as MM wave and it has wavelength of 1 mm to 10 mm. This is a great possibility that 5G may move wireless signal to that range of a high frequency band, as it is going to open up a huge amount of bandwidth and alleviate concern on wireless traffic congestion. So, why in the beginning no one is using this band of spectrum for cellular communication? And to answer this question, we need to know the characteristic of MM wave. Generally, as you move to a higher frequency, transmission range gets shorter, hundreds of meters rather than kilometers, and signals are unable to penetrate wall that easily. Secondly, some hardware components such as analog to digital converters might also be expensive. Also, other challenges is if the transmitter and receiver don't have a line of sight, there is a lot of attenuation in the signal. However, not good for long distance, but they are excellent in short distance application. As mentioned in the earlier slides, there has been a trend towards smaller cells. mmWave can take advantage of this technology, as they are better suited for transmission over relatively short distance. High frequency signal can also be reused across short distance by different cells in a network, meaning the available spectrum is used more efficiently. In addition, antenna size is inversely proportional to frequency size, so higher frequency signal would require smaller antenna. You could pack more antenna into the device. That enables directional transmission. You could actually stir the signal in a particular direction. This could overcome the loss of some of the signal transmission strength. More than one antenna operating in the same frequency range can also send multiple streams of data to increase the data rate. So, through mmWave, we come to the next key technology that I wish to discuss. However, the application of MIMO technology is very wide, and in my presentation, I will only cover how the use of massive MIMO could improve the performance of mmWave. So, mmWave is a potential technology for 5G. This means we will use extremely high frequency. In this case, the size of a single antenna will be very small, and the area for receiving energy will also be very small. So to overcome this small aperture on the receiver end, we need to use large number of transmission antenna. So what other benefit could we gain from using massive MIMO in related to mmWave? Let's take a good look at our situation using the free space model approach. From the Friese equation, we know that the receive power is affected by the distance, transmit power, frequency, transmitter and receiver antenna gain. According to this equation, the receive power is in proportional to the square of the wavelength. For example, if we assume the antenna gain does not change, the frequency gets increased by 2 times. This means that the wavelength gets shortened by 2 times. The receive power will get decreased by 4 times. As mentioned before, we will use much higher frequency signal in 5G network. It means the receive power will be much lower than in the current communication system. Take an example. If we are using 2 GHz frequency in the current communication and we will use 20 GHz frequency in the 5G communication system, the wavelength in 20 GHz is 10 times shorter than the wavelength of 2 GHz. It means the receive power at 20 GHz will be 100 times lower than the receive power at 2 GHz, and this is super bad. So we have to fix these situations. Now let's think of how we can overcome this drastic receive power reduction at high frequency. So let's take at the first option, increase transmitter power. Yes, we can do this till a certain extent, but we cannot keep increasing the transmitter power as we like, as we don't want to fry our head. Second, decrease the distance between the transmitter and receiver antenna. This cannot be a solution since we cannot change the distance as we like. Third option also does not seem as a viable option, as we are using extremely high frequency for 5G network. So we only left option 5 and 4, and this is to increase the receiver antenna gain and also increase the transmitter antenna gain. So in mmWave, the wavelength is very short, meaning the value of lambda will get very small, and this lead to the decrease of receiving power. And how can we resolve these issues? As mentioned earlier, when we are using a very high frequencies, the size of the antenna will be very small. Hence, we can use more antenna for transmitting and receiving on the devices. And this is how massive MMO can improve the performance of mmWave in wireless communication system. Basically, with more number of transmit and receive antenna, the gain will be higher. Now I'm going to talk about the concept of mobile femtocells, also known as the M femtocells. The concept of M femtocell is very similar to femtocell inside a building. It is a small cell that moves around and dynamically changes its connection to an operator core network. Basically, it is installing a mini base station on the transportation, and group of users inside the vehicle will be served by the M femtocell instead of the outdoor base station. They are viewed as a single entity to the outdoor base station. We can see femtocell as some form of mobile relays that help us to communicate with the outdoor base station. There are two great advantages of using M femtocell in transportation. First, it reduces the signal overhead for a variety of network operation. For example, handover is done by the M femtocell only for all its associated users inside the vehicle. This greatly reduces the handover activities. Secondly, the battery life of the mobile devices is prolonged as there will only involve short distance communication with their serving M femtocell instead of the long distance to outdoor base station. Here we comes to the fourth key technology for 5G network. With regards to conventional MIMO technology, a new revolution modulation scheme was invented using multiple transmit antenna to achieve space diversity. Spatial modulation has significantly improved the spectral efficiency by spacing multiple transmit antenna apart to gain a third dimension in signal consideration diagram. This allows transmission of more data bits using the same amount of spectrum bandwidth, and this makes it more spectral efficient. Also, spatial modulation only activates a single transmit antenna at particular transmission instant, and hence it only requires one RF chain as compared to conventional MIMO shown in this slide. This reduces RF hardware complexity, size, and cost. By requiring only a single RF chain, despite number of transmitter antenna available, it maintains the constant power usage. This has significant advantage in energy efficiency compared to the conventional multi-RF chain MIMO configuration. As mentioned in the earlier slide, the use of multiple transmit antenna will create a space diversity because signal is transmitted over several different propagation paths. With these properties, this allows the representation of the third dimension in signal consideration diagram as shown in this slide. For example, we want to send the stream of data BACD. It will only take two intervals T1 and T2. In T1, transmit antenna 1 will be used, and in T2, transmit antenna 4 will be used. As we all know, the radio spectrum frequency is allocated for different wireless technology like GSM, TV, wireless LAN, military usage, and long-term evolution. However, fixed spectrum allocation is a wasteful of resources, as spectrum utilization depends strongly on time and place. Hence, we come to our last key technology for 5G network that I'm going to discuss. It is called the cognitive radio. It is a form of wireless communication technology in which a transceiver can intelligently detect spectrum bands that are in use and which are not. When allocated spectrum is underutilized, it will have a lot of spectrum holes. A spectrum hole is a band of frequency assigned to a primary user, but it was not utilized by the user at that particular time and specific geographical area. The basic concept of cognitive radio is to make use of spectrum sensing technique to actively monitor the spectrum band, capture their information, and detect the spectrum holes. The characteristics of the detected spectrum holes are estimated, and appropriate spectrum band is chosen according to the characteristics and user requirements. Once the operating spectrum band is determined, the transceiver communication parameters will be dynamically configured and communication can be performed over this spectrum band. The allocation of unlicensed users to those unused bands increases the spectral efficiency. There are research shown that spectral efficiency is lower when there is a high number of primary receivers. This somehow implies that cognitive radio might be more appropriate for rural areas where population is less dense. There are also other considerations about coordinative radio like security concern where malicious user can modify its air interface to mimic a primary user to steal information. Also, the trade-off between sensing time and data throughput is also a big concern. After all, cognitive radio are using spectrum band that is allocated to licensed users. Spectral sensing must be fast and accurate to minimize interference with the licensed users and maximize the data throughput. However, this is not an easy task as there are many uncertainties in the world of wireless communication. However, these challenges will not be discussed in this presentation. With this, I come to the end of my presentation. To summarize everything, the current approach for 5G network is to improve the cellular architecture by separating indoors and outdoor usage, so it can rely on the existing indoors wireless technology like visible light communication, DAS, Wi-Fi, etc. for cellular communication. Ease the workload of the macro cells base station through overlay cells, and in result of this will also increase the system capacity, spectrum reuse, and achieve higher data rate in smaller cells. Next, for the use of key technologies, we have talked about the use of extreme high frequency to achieve high data rate in small cells, using massive MMO to improve the signal gain, using M-femtocell to improve mobility on transportation by dedicating network operation like hands-off. In spatial modulation, we see how using additional hardware can convey additional information, and lastly, using coordinative radio to reuse of allocated spectrum when it is not utilized. It would seem that the current approach is to shorten the communication distance by bringing the base station closer to the devices. This will allow the possibility of using mmWave. The use of additional hardware to improve spectral efficiency is also a viable option for 5G network. So, thank you for watching this video.